Hello, I'm Dr. Julie Kodev, and this is Martini Human Anatomy, Chapter 15, the nervous system. Specifically, we're going to be talking about the sensory and motor tracts of the spinal cord today. Now, this is a functional MRI. Over here on the right, it looks like a beautiful piece of artwork, but it is actually a functional MRI of the brain. And you can see some of these ascending and descending pathways of our central nervous system here. Our outline and objectives for this chapter, we're going to look at the anatomy of a cross-section of the spinal cord. We're going to look at gray and white matter, and we're going to talk about spinal tract vocabulary, and we're going to look at the specific ascending and descending pathways. Our introduction here. So on the left, we see another functional MRI of the pathways going down and up the spinal cord and the way that the information sprays out along the cortex. So millions of sensory neurons are delivering information to the central nervous system all the time. Millions of motor neurons are causing the body to respond in a variety of ways. Our sensory and motor neurons travel by different tracts in the spinal cord here. This is the anatomy of the spinal cord, and you can see the cervical vertebra here. This is the spinous process. This is the front of the body. This is the back of our body. And then this is the transverse process area over here. And the vertebral body and the spinal disc would be right on top of this area right here. Okay, so this is the spinal cord. That's our spinal cord right there. And the inner area, that's the gray matter right here. It's kind of butterfly shaped or H-shaped. And then this outer area here is the white matter. And then we can see the nerves here. Let me get a better color to show. You can see the nerve come out right here. Okay. Good. So gray matter and white matter. So gray matter is going to be the collection of cell bodies and dendrites. Okay. In the brain, note that the gray matter is all around the cortex, and that white matter is in the middle area here. There is some gray matter nuclei, cell bodies, deep within as well. Okay? But the cortex itself is made of gray matter. And then over here on the spinal cord, on the right-hand side, we have gray matter in the middle, surrounded by white matter. Okay. Gray matter is unmyelinated because what makes white matter white? Myelin. Okay, so gray matter is unmyelinated. It is just this collection of nerve cell bodies and dendrites. So this area right here is going to be the gray matter. Let's put that in red. Okay, so this area here is going to be the gray matter, and then this area here is going to be the white matter. Okay, so over here on the right of this stained cross section of the spinal cord, this is the gray matter in here, no matter what color it is stained. Okay, and then this is the white matter around here. Now, what makes white matter white? That's myelin. What makes myelin? Okay, so myelin in the central nervous system, remember that's the oligodendrocytes. In the peripheral nervous system, it's Schwann cells. So we use this mnemonic: central oligodendrocytes, peripheral Schwann cells. And we saw this picture before, this oligodendrocyte cell here attaching to the axon nerve fiber in light green over here. And we're looking at the myelinated, non-myelinated nerve fibers, allowing for communication between our brain and our cord. And it's going to run in three directions. We're going to see ascending or going up. Okay, so ascending or going up to the higher centers of the brain. This is the sensory input. It's going to be sensory, afferent or ascending, and dorsal. That's going to be the dorsal area of our spinal cord. Okay. Descending, okay, from the brain to the cord or lower cord levels. This is going to be motor or our movements. Transverse would just be from one side to the other of that spinal cord segment. Subdivisions of white matter, we're going to use these terms: fasciculus, lemniscus, funiculus, and tract. So what is a fasciculus? You've heard this before with muscles, right? So we see this fascicle, right? And we saw this bundle of structures, okay, like the muscle fibers or the nerve specifically, right? And what we're going to see over here is the dorsal columns, this right here, this blue area back here, that's dorsal or towards the back, posterior. Our dorsal columns are also called the posterior columns. And they have these two interesting names, fasciculus cuneatus and fasciculus gracilis. So these two columns right here, FG, I wrote on there for you. That's fasciculus gracilis and then fasciculus cuneatus. These are the fasciculus or the bundles, and we'll get into the specifics of those in a moment. Right now, we're just defining some terms. So, the medial lemniscus. Okay, so medial lemniscus. Lemniscus just means ribbon. Okay, just means ribbon. And it sure looks like a ribbon over here on the right in this functional MRI of the medial lemniscal pathway. So it's a ribbon. This just means ribbon in the middle. And it is. Okay, so it's just a middle ribbon. And we're going to combine these things so that dorsal column on the slide just before this one and the medial lemniscus. Okay, so the dorsal column, medial lemniscal pathway. This sensory pathway of the central nervous system conveys sensations like fine touch, vibration, 2-point discrimination, and proprioception from our skin and our joints. Now, funiculus just means cord-like structure. So we'll see this over here. So posterior funiculus. So sometimes those dorsal columns we call posterior funiculi, and then we'll see anterior funiculi area over here, and then you can see the lateral funiculi here as well. So how are we naming things? So this is pretty complex at first, when you first hear all of these terms, but we're going to look at some of these terms coming up and it'll make a little bit more sense. So we see spine and we see cerebellum here. So we're looking at this tract. Okay, so tract, this group of axons that have a common origin and destination. There's two parts to the name, right? So we see a spinocerebellar tract. So it's coming from the spine and going to the cerebellum is all that means. Okay, the first part of the name refers to the location of the neuronal cell bodies from which these axons originate. The second part refers to the site where they terminate. Okay? Spinocerebellar tract. So again, spinal cord up to the cerebellum. Okay. Spinal cord is involved in sensory processing, motor outflow, and reflexes. So we see the sensory input information gathered by sensory receptors about internal and external changes in our body. And then this integration with this processing and a motor output. So just like we saw it here before, we also see it in the spinal cord. Okay, so we're going to have that same component here. So when this the cord gets a little complicated, just kind of remember the way that the brain is doing it and the simplicity of this picture here. Okay. So 4 key points about spinal tracts and pathways. This word right here, decussation, means it crosses over. Desiccation means something's dried out. Well, we're going to talk about decussation or crossing over. Okay, so if something comes over here and then crosses over to the other side. We're going to talk about relays consisting of a chain of 2 to 3 neurons, kind of like power cords kind of strung together. And then somatotopy, precise spatial relationship in central nervous system correspond to spatial relationship in the body. And then symmetrical pathways. So everything is bilateral and symmetrical, even if it's not labeled as such. Everything here is bilateral and symmetrical, even though it's not labeled that way. So we have this crazy looking system here. So we're looking at the spinal cord here. Okay, this whole thing is the spinal cord. This is a cross section of the spinal cord, and it's about as thick as maybe your thumb, how thick your thumb is. So if you look down at the width of your thumb, that's the width of the spinal cord. So it's really amazing that they found all these tracks and all of these areas here. You don't have to memorize this. This is just a cool picture to kind of give you perspective of how small these information superhighways, these pathways are within the spinal cord. This is a glossary page that I made for you. You do not have to study from this page. It might be a difficult page to look at first, but it might be an easier page to look at when you're studying later. We're going to look at these tracks right here. So we're going to look at some of these tracks that go up or ascend, and then some of these tracks here that descend. So figure 15.1 in your book gives you a nice clear picture here. So here's your posterior dorsal columns, gracile, fasciculus, and cuneate fasciculus. Note that they're called that here, but we also call them fasciculus gracilis and fasciculus cuneatus. It's just a matter of what you are reading at that moment in time on what they decided to call it. And then we see the spinocerebellar tracts in yellow over here. And spinocerebellar from the spine to the cerebellum. There is a posterior in the back and an anterior in the front. And then we see this one here. We see our spinothalamic tract, so from the spine to the thalamus, and we see a lateral and an anterior. And we like it when posterior goes with anterior. That makes sense, right? But then we're like, wait, lateral usually goes with medial, anterior usually goes with posterior. It does, but what we're looking at here is this is lateral on the cord. This is anterior on the cord, and that's why they named it that way. Okay, so this is the anterior aspect of the spinal cord. This is the posterior or dorsal aspect of the spinal cord. Here's another one to look at here. And I have a blank screen on the next one here, so you can pause and fill this one out in order to kind of digest these words and kind of make them real, right? Because they're kind of odd words at first, but you'll get used to them. So pause and go ahead and complete this so you at least know what these words are as we move through. Okay, so that was a study technique that I always used for myself. So whenever I saw words that just looked overwhelming, I would just stop and I would write them out a couple of times until they looked a little bit more familiar. So pause and then come on back. So we're going to look at these sensory tracts, these three major sensory tracts that we're looking at. Again, spinothalamic, dorsal columns, spinocerebellar. All three of these tracts are also called somatosensory tracts. Information goes to the central nervous system on these tracts. This is a picture from your book here, so let's go ahead and unpack this. So what we're going to look at here are these first, second order, third order, first order, second order, third order neurons. Now what this looks like to me, whenever I look at these, whenever I teach these, this is like extension cords. Okay, where are they plugged in together? Okay, so we've got one coming through here, and it plugs in to the next extension cord right here. And then it plugs into the next extension cord right here. So you'll see the first order end here and the second order begin here. And the second order end here and the third order begin here is all that this is saying. So our spinothalamic tract, sometimes you'll see it as anterolateral system or ALS. And what you're looking at here is the lateral and ventral spinothalamics. So lateral and ventral spinothalamic. Lateral spinothalamic tract specifically is going to deliver pain and temperature sensation to the brain. Okay? Ventral is for light touch and pressure. And both of these are going to cross over. If you look over here, it's going to cross over right here and then go up into the brain. So it crosses over immediately. Where it's crossing is this little spot right here called the substantia gelatinosa. You don't really have to remember that one. After it crosses over, okay, we're going to look at this area here from the spinal thalamic tract, okay, to the medial lemniscus, that blue ribbon that we looked at before. Okay, so we're going to see the nociceptors, pain receptors, the temperature receptors coming in, okay, and then we're going to see its synapse here or connect here and then go up that medial lemniscal pathway with the dorsal columns, and then it's going to synapse here at something called the VPL of the thalamus, which is a special little nucleus in the thalamus. Thalamus is right here. And then it's going to go up into Brodmann's area 312, which is somatosensory, and or we can really just call it the primary somatosensory cortex. So what is that, right? So it's crossing over here at that substantia gelatinosa. So it comes into the cord and then crosses over and goes up. And then this is the thalamus. And then that VPL of the thalamus is this little jelly bean right there. Okay, so spine to the thalamus. Spinothalamic is all we need to remember from this. So what are we looking at here with that 312 of the brain? Okay, not 1, 2, 3. So these are called Brodmann's cortical areas. And for some reason, Brodmann numbered these in a very weird way. And then somehow no one corrected him, and we all just went with it. And this was over 100 years ago, so there's no real change in it at this point. Okay, so what we look at here is this is the central sulcus right here. Okay, so in between this color pink here and then this lighter purple here, this line through here is the central sulcus. Okay, so what does that mean? Everything in front of it is going to be more concerned with motor function in the frontal lobe right there. And then this right here is going to be more concerned with sensory. So see the motor function for this pink area here and the somatosensory for this purple area right there. Okay, so that's all that means. Executive function right here is really just like who we are as people, how we think, our personality, things like that. And so this area right here and this area right here, okay, are over here, and you can see they kind of flip it around, and this is the motor area, this is the sensory area, and then we call this homunculus man. So see the person in here? Okay, so we see the face, we see the hand, we see lower extremities, and so there is a somatotopy or a map of who we are as people here in our brain. So that information comes up and hits right here for sensation for our hand. Movement from our hand, the command center is here and then descends that way. It's pretty cool, huh? All right, spinal thalamic tract, touch, pain, temperature. Okay, so the ability to feel temperature. Okay, why do we put a hot pack or sit in a hot tub to decrease pain? Okay, why do we, when we bump our knee on a table, right, we rub it, right? That touch sensation will decrease the pain sensation. Okay, same thing with icing. That temperature sensation will decrease that pain sensation. So that hot and cold will have physiological effects that we don't really get into in this, but I put a little slide here if you wanted to look at that. Increasing blood flow if it's heat, decreasing blood flow if it's cold, right? But we think more along the neurological events of it's another message on the line. Right. So if you're listening to me right now, and then there were two other people talking to you at the exact same time, it would be hard to concentrate on one thing, and that one message of pain would not be getting through as easily, right? Because you'd be listening to temperature and you would also be listening to this right here, touch, pain, temperature. Okay, those three different things. So some of the temperature, okay, components, we use this in our pain control, right? So we'll put on icy hot. So your body's like, wait, is this icy or is this hot? I don't understand this temperature change, right? And so what that's going to do is that's going to, again, put too many signals into the spinal cord. Right. And the body's like, well, I don't really understand if this is hot or cold, but I don't really feel the pain anymore because I'm distracted by the temperature change. Same thing for this biofreeze for the feeling of cold, and this capsaicin, which comes from red hot chili peppers for arthritis pain relief, giving you the sensation of heat. Okay, Chinese medicine uses this as well in its liniments, and this is a cool liniment called Po some on. Just sounds like porcelain, right? And this pink here denotes that it is a hot or a warming solution that you can put on your skin. This here is blue, so it denotes that it is a cooling liniment that you can put on your skin. Dorsal columns, that's that fasciculus cuneatus and the fasciculus gracilis over here. So what are we doing? Fasciculus gracilis is all about the lower extremity. Transmits information to your cerebrum coming from areas below T6. Fasciculus cuneatus is all about your upper extremities or areas superior to T6. Both of them, okay, it's both fasciculus gracilis, both fasciculus cuneatus, are going to give us conscious proprioception. Proprioception is position sense, or where are we in space? Kinesthesia, movement, right? Feeling movement, vibration sense, 2-point discrimination. Both of them are going to ascend, go up ipsilaterally. Ipsilaterally means same side. Contralaterally would mean opposite side. So ipsilaterally in the spinal cord, it's going to cross over at a specific spot in the medulla oblongata of the brainstem. It's going to go up that medial lemniscal pathway as well as that spinal thalamic, right through that medial lemniscal middle ribbon that we saw, up into the thalamus and into that same sensory area of this right here. Okay, this Brodmann's 3-1-2 area or here. Okay, so if it's hand, it's here. If it's foot, it's landing over here. So gracilis should sound familiar, right? Real easy to remember that it is lower extremity because we have a muscle called gracilis, right? It's that groin muscle, gracilis. So it's really easy to remember that that's the lower extremity. Okay, so the lower extremity and then the pathway it takes up into the brain and then homunculus man right there at the foot. Great. So spinocerebellars, from the spine to the cerebellum. This is going to be unconscious proprioception or position sense. So knowing where we are in space without having to think about it. This is going to be our muscle spindles who are in charge of stretch, and our muscle GTOs or Golgi tendon organs, which is in charge of tension. We have two sets. We have a dorsal spinal cerebellar and a ventral spinal cerebellar. Okay, so this dorsal spinal cerebellar, that's going to stay on the same side. The ventral spinal cerebellar is going to go to the opposite side. The rest of it we don't really have to worry about, except for the concept here of it being same side and going through inferior cerebellar peduncle, and then opposite side and going through superior cerebellar peduncle. This is redundant or repetitive on purpose. So if something goes wrong with one, hopefully we still have the other intact, so we can still understand where we are in space and how much muscle stretch and tension is happening to our bodies. So there's just a checks and balances that's happening here is all that that means. All right, so we are through our sensory tracks here. We're moving into our motor tracks, also known as efferent. Afferent was sensory over here. And now we're moving into this area here. Now, remember, it's bilateral and symmetrical and not color-coded in the real body. So right over here. So in our book in Martini, we see this organization of the motor tracts. These somatomotor tracts always involve at least two motor neurons. An upper motor neuron, whose cell bodies lies in the central nervous system, brain and spinal cord, and a lower motor neuron located in a motor nucleus in the brain stem or spinal cord. Activity in the upper motor neuron excites or inhibits the lower motor neuron. The axon of the lower motor neuron extends to the skeletal muscle. This is what's going to make that muscle fire or contract or move. Okay, it is only capable of exciting skeletal muscle fibers. Okay, so you can see the upper motor neuron deliver motor commands to motor nuclei in the brainstem cord. You can see this pathway right here. Here's the homunculus man again. And that information, this is motor, so it's going to go down, descending. Okay. So motor fibers distributed to the motor nuclei of our cranial nerves, right, are grouped within what we call cortical bulbar. Bulbar is going to be for our face. Okay. Cortical spinal is going to be for the rest of our body. Now over here, number 2, lower motor neurons relay motor commands from the central nervous system, motor nuclei to our skeletal muscles, like your bicep, okay? Skeletal muscles. So you can see the brainstem here, brainstem from the top down is midbrain, pons of medulla, and then we see the decussation. Remember, that means crossing over. Okay, so crossing over, and then we see spinal cord here and ventral pathway to the skeletal muscles. So a little bit more here for our descending motor tracts. Our subconscious and conscious motor commands control our skeletal muscles through descending motor tracts within our spinal cord. So what are we looking at here? Motor tracts carrying subconscious motor commands. So we're going to look at the rubrospinal tract. Okay, rubrospinal tract automatically adjusts upper limb position and muscle tone during voluntary movements. We're going to talk about these a little bit more in depth in a moment. The medial reticulospinal tract originates in the reticular formation, which is a diffuse network of neurons in the brainstem. The functions of the tract vary depending on which area of the reticular formation is stimulated. Tectospinal tracts control reflexive changes in position in response to auditory or visual stimuli. So auditory being hearing or visual being seeing. Okay, so you hear something out of the ordinary and you turn and you look. You see something out of the ordinary and you turn and you look. That is this right here that is in charge of that. Okay. The vestibulospinal tract, vestibular is all about our balance control. Okay. So vestibular tract carries motor commands that reflexively control posture and balance. Over here, we can see anterior cortical spinal tract contains axons that do not cross in the brainstem. And here we can see lateral cortical spinal tract containing motor fibers that do cross. Okay, so it's about an 80-20 system. So about 80% are going to cross, about 20% are not going to cross. Sometimes you'll read 90% and 10%. So it's the majority and then a smaller amount. And let's take a look. So we see these cortical spinal tracts, and you can see it over here in a functional MRI that's moving around. That looks pretty cool, right? So that's from the cortex to the spine, and it takes this pathway through here if you wanted to know, okay? And then it's going to synapse in our spinal cord, okay? And then 80 to 90% is going to cross, and it's responsible for fine motor control, okay? And then 10 to 20% stays on the same side. It's responsible for gross motor control, or the big movements that don't take a lot of skill. Fine motor control is all about skill. And here's another picture of it for you. Cortex, crossing over at the medulla, and then going through the cord or staying the same side. And then over here again, functional MRI of it. Pretty cool looking. So we can see the cortex here and then the pathway down this way. Pretty neat, those functional MRIs. This right here in pink, oops, this right here, that little U in pink right there, that is the corpus callosum. That's connecting your right brain to your left brain. Pretty neat, huh? But the corticospinal tract is this here in blue. And you could see it here as well. Okay, so this table is from your book. And so you could see the cortex, okay, all the way down. Okay, to our skeletal muscles, we're going to go through midbrain, pons, medulla, and then the pyramidal cells here. And the decussation of the pyramids, that is just the crossing over, okay, of the corticospinal tract. Sometimes is going to be called the pyramidal tract, okay? They just like to give nicknames, okay? The pyramidal tract, because the cells look like little pyramids. Yeah. Okay. And then some of it's going to cross over here and then go out to the skeletal muscles. Some of it's going to stay on the same side. So here's our slide reminding us of this. So this is the pons. This is the medulla right here. So that's the brainstem that we're looking at. And here are the pyramids of the medulla. Okay. And so what we see down here is the pyramidal decussation, or this little puckering happening right there. That's the crossing over of the pyramidal tracts or corticospinal tract. Okay. So these upper motor neurons over here, those are the pyramidal cells in that primary motor cortex. Those lower motor neurons, that's the ventral horn and the spinal cord, and that innervates our skeletal muscle. Okay. Sometimes you'll see it called direct pathways. Those are the pyramidal tracts or corticospinal and corticobulbar. This is motor to your body. This is motor to your face. Okay, so move the body, move the face. Sometimes you'll see them called direct pathways. Sometimes you'll see them called pyramidal tracts. It's all the same thing. So frustrating to try and learn, right? And then sometimes you'll see other things called the indirect pathway. That's all the other motor pathways, okay, besides those two. Great. Corticobulbar, that is to move your face. Okay, so move your face. So it's going to follow the same path as corticospinal till it goes to the midbrain of our brainstem. And then it's going to go out to our cranial nerves, 3 through 12, except for 8. Okay. So this is going to move our face via cranial nerves. Next up, we see vestibulospinal tract. We're going to look at lateral and medial, and for our exams, it's just going to be the same thing. Okay, so it starts in the vestibular nuclei. I show you over here what that is, what we're looking at over here. This is midbrain. Right? This is pons area. What we're really looking at here is that the cerebellum has been cut away. So these are the cerebellar peduncles. And then down here is going to be medulla territory and then spinal cord. Okay. And so it starts at the cell bodies for the vestibular nuclei of the lower pons and medulla. It stays on the same side through the medulla, and then it synapses at the motor neurons in the anterior horn. What's it do? It coordinates head, eye, posture, and balance. So we can walk around, we can turn our head, and we can move our eyes to focus on different objects and still keep our posture and our balance and not fall over. So as we see here, we see Simone Biles giving a very good example of great vestibulospinal tract control over here. And when we need to regulate our balance, I had to look really, really hard for her losing her balance a little bit here, right? So when we start to lose our balance, this vestibulospinal tract is going to excite our extensor muscles of our neck, right, and our back and our upper limbs. Okay, so you can see right here, her tricep or the extensor muscles firing off, or when we just wave our arms to try and get our balance. That's vestibulospinal tract doing that for us. Okay. Now, rubrospinal tract, we saw that one mentioned. Rubro, okay, ruby red. Okay, ruby red. It's the red nucleus. Okay, the red nucleus of the midbrain. This is a motor pathway that's going to connect the cerebellum, okay, to the red nucleus of the midbrain. It's going to go through all these pathways, and what it's going to do is it's going to give us this flexion protection, or you might have seen this with a stroke. Okay, so this classic stroke appearance, okay, is what happens, okay, when we see that rubrospinal tract flexion protection dysfunction. Okay, so this is the red nucleus right here in the midbrain. Okay, and maybe we're feeling like Homer Simpson here, right? And his flexion protection of the red nucleus and the rubrospinal tract. And check it out. He's on a red nucleus, a red circular carpet. I don't think that's coincidence. The Simpsons were pretty cool that way and hiding little Easter eggs like that. So that area can also be called the tectum, so inferior colliculus and superior colliculus, or our visual startle response, okay, is superior colliculus. Okay, so what is this? This is motor efferent head and neck movements in response to visual stimulus. And remember, I mentioned that a little earlier. You see something out of the corner of your eye, you turn in your look. That is coordinated by tectospinal. Just like this little girl. Okay, so we see her reacting to this dolphin that should not be there, right? That makes no sense to her why this creature would be right there in space. And so that's superior colliculus creating that reaction. And so that's that green component right there. That's the midbrain area right there. That's tectum right there. Okay, so superior colliculus, inferior colliculus, those are the tectum of the midbrain. Okay. So also, you'll see it called corpora quadrigemina, quad being four, corp being body, four body. Okay. They get real tricky with their words, don't they? So again, superior colliculus, she saw something out of the corner of her eye, she turned and she looked, and we either escalate up with our fight or flight response or de-escalate down because we're like, oh, we're safe. Well, she did not feel safe, right? So you could see her cranial nerves going off, right? So her facial nerve making her face all scared, and cranial nerve 11 bringing that shoulder up and into her ear by activating levator scap and SCM. Okay. So that's the tectum right there. Right, figure 15.6 in your book, nuclei of the subconscious motor pathways. So we look here over at the basal nucleus, consisting of the caudate nucleus, putamen, globus pallidus, a little bit more than just that, but that's a good representation right there. And then we see the red nucleus. We just talked about that. Homer Simpson rolling around on that red carpet, inflection protection. You can see the tectum that I was just talking about here of the midbrain. This is midbrain right here. Okay. And then just below that is going to be pons. Okay. Pons. And then just below that is going to be medulla of the brainstem. Okay. Good. So levels of somatomotor control, that's going to involve the cerebral cortex, that motor cortex, that homunculus man that we saw, our basal nucleus, and our cerebellum. Okay, so our three main components right here: motor cortex, basal nucleus, and cerebellum. And then we're also going to have hypothalamus, pons, medulla, brainstem, and spinal cord, which pons, medulla, and midbrain are the brainstem, and the spinal cord and the thalamus get involved as well. But these are the big three right here. So those coordinate our movements. So we can see basal nucleus here, modifying voluntary and reflexive motor patterns at the subconscious level. So what basal nucleus does is it's kind of the calming hand on a shoulder, or it's the leash on a dog. Okay, and the dog wants to run. And what the basal nucleus does is it stops it from running. Okay, so otherwise we'd be moving excessively. So it slows down and controls our movements that way. Cerebral cortex is the dog, right? That it's like, hey, let's go, right? Where the basal nucleus is the leash on the dog. So this is going to create the movement. This is going to control the movement through inhibition. Hypothalamus, that's where neuro becomes endocrine, and this also controls reflex motor patterns related to eating, drinking, sexual activity, modifies respiratory reflexes, and then pons and superior medulla oblongata control reflexes of balance and complex breathing activity. And then we see our brainstem and spinal cord controlling simple cranial and spinal reflexes. The lower part of the medulla oblongata controls a lot of our basic respiratory activities. So upper is complex, lower is basic. And then we see cerebellum coordinating complex motor patterns. That's really going to be a lot of our balance control and course correction, right? So that feeling of you thought there was one more step and there wasn't, or you thought there wasn't a step and there was. That cerebellum is going to smooth that movement out for you and hopefully keep you from falling. Thalamus, everything goes through the thalamus. Everything comes up through the thalamus and then sprays out into the cortex. Cerebral cortex plans and initiates movement and motor activity. So our somatomotor control, okay, is what we're looking at here. So somatomotor control involves a series of levels with simple spinal and cranial reflexes at the bottom and complex voluntary motor patterns at the top. B, the planning stage, when a conscious decision to move is made. So we've decided to move, right? Information is relayed from the frontal lobes to motor association areas. These areas then relay the information to our cerebellum and our basal nucleus. C, movement. As the movement begins, the motor association areas send instructions to the primary motor cortex. Feedback from the basal nuclei and cerebellum modifies those commands, and output along the conscious and subconscious pathways directs involuntary adjustments in position and muscle tone. Excellent. So we not only used Martini, which is cited at the front, but I also used a lot of Marib and then a couple of extra neurology books for some other pictures and clarifications. So good job getting through. This is a tough subject to master. So good job getting through it, and I'll see you for the next chapter.